Hello, this is a lecture about tables and graphs. Our today's lecture objectives are to know all the parts of the frequency table, to be able to identify the different types of graphs and when it is appropriate to use each different type of graph, and finally, how do we describe a distribution. So what is the main difference between tables and graphs? Well, this is a table, for sure you have seen those, but this is a statistical table, and this is a graph. So a frequency table usually contains numbers, and a graph on the other side is a visual representation of those numbers. Frequency tables. So frequency table is a very convenient, concise way of displaying data. SPSS is excellent for generating frequency tables. It makes a very difficult job very easy. Any of you who have taken statistics before and have actually drawn frequency tables by hand, you know that is a little bit of a pain to do so, but SPSS it's literally a click of a button. So anyhow, what do we use them for? It truly displays all the possible answers and frequencies for a variable. So in this example, you having respondent's occupation. You're asking people, what do you do for a living? And you're trying to pretty much figure out what the average person does out there and calculate some frequencies and percents based on their responses. So your total sample was 952, and this is where I know that. Always on the very end of your frequency, you're going to be running a total. So total is 952. Out of those, 54 are your farmers. So this is the frequency. You had 54 farmers in total. 4 were professional, 29 were business people, and so on and so forth. Then you take that frequency and you calculate, you turn it into a percent. So you want to find out of all the different occupations that you're having, what percent corresponds to farmers, for example, or what percent corresponds to professionals. So you would be taking the 54, you're going to be dividing it with 952 times 100, and you're going to be getting your percent. Valid percent is very similar with percent, but it takes into account any missing responses. And what do I mean by that? Have you ever been stopped and been asked to take part in a survey and you kindly said, yeah, no problem. And once you opened the survey, you were kind of in a rush and you realize that you have to answer 50 questions, so you kind of like start like answer the questions, but then you skip half of them because you want to get out of there as soon as possible. So in this particular case, when the researcher is going over your answers, they're going to run into a little bit of a trouble because you are counting as a participant to the research, but then you left blank a bunch of questions. So truly, they do not know um, what your responses to those questions are. So those are missing responses, but you are a participant. So valid percent will depict that. It will take into account any missing responses. And that's why sometimes if there's missing responses, you're going to see a slight difference between your valid percent and your percent. Now, this is a very important slide. What I want you to pay attention here is what goes inside a frequency table, okay? So a frequency table has to show the frequency, okay? So frequency, what do we mean by that? That is the number of participants in each single category, okay? Percent is the percent of participants in each category. As we said, you take the frequency and you turn it into a percent in order to be able to find out what percent is represented out of the total. Valid percent will take into account also your missing responses. So SPSS is actually excellent for making those adjustments. If you had to do this by hand, would be a little bit painful, not undoable, but painful for sure. And finally, cumulative percent would be you're running total. Okay, so here you would be adding your percentages as you keep going, and we're going to see an example for that. Here's another example of a frequency table. We're gonna revisit this data set again when we're gonna have an SPSS tutorial. Anyhow, what we see here is the question is if our participants believe in aliens. So there, any possible responses would be either I don't believe in them, there might be something out there, I have no opinion whatsoever, there's definitely something out there, and I have met them. So out of the 25 people, and I say 25 here, this is my grand total of frequency, so that means I asked 25 people. 5 of them do not believe in aliens. 8, they say, well, there might be something out there. 5 have no opinion. Another 5, they say, well, there might be something out there. And finally, 2 people actually have met them. The next step would be to calculate the percent. And the way you calculate the percent is the way you always do, which is you take the number, the frequency of that particular category, and you divide it over the whole. So 5 over 25 times 100 to turn it into a percent, that's 20. 8 over 25 times 100, it's 32, and so on and so forth. Now, in this particular case, you're going to notice that there's no difference between your valid percent and your percent. The reason being is that you do not have any missing responses. That means out of the 25 people that you interviewed, all 25 answer all the questions. Cumulative percent, as I said before, is a running total, and the way we calculate that is as follows. So I like to carry over the 20, which is the first percentage right here, into the cumulative percent column, and then I keep adding the next to it. So I kind of like go in a zigzag mode. So 20 plus 32 equals 52. I write 52 right here. 52 plus 20, 72. 72 plus 20, 92. So as you keep going, you keep adding the next percentage, and you're always going to end up with 100% at the very end. Now you're probably thinking, well, what in the world do I need the cumulative percent? Well, this is a very simple example, but there's a possibility that you have a much more complex table, and usually you tend to put your categories in some kind of an order. And what you can see here, for example, we can say that 72% of our participants, which is this running total right here, either do not believe in aliens or have no opinion, but they definitely do not have a solid belief in aliens, right? So instead of just going here and adding those numbers, we can just simply go up to the level of no opinion and draw a line across and realize that this is 72% of our participants. Last thing that I want you to pay attention to is the labels. Sometimes you might see frequency as an F, percent as a P, or a valid percent as a VP. Don't get confused. Just be aware that sometimes you're not going to see the entire word there. I might give you something like that in a test, so just be aware that F stands for frequency. Now, the question is when it is best to use a frequency table, okay, with what kind of data? Well, the best type of data would be nominal. That would be the ideal, simply because you usually tend to have a few categories, so it's not going to be very complex and very busy. Ordinal are tricky. Can you think why ordinal would not be appropriate for frequency tables? Well, frequency tables have a few rules, and one is that they're either solid categories, they're not connected, and if they're connected, they have to have an equal distance between them. By definition, ordinal variables, the distance between each category is not equal. So that would make it very challenging in order to create a frequency table with ordinal type of variables. Now, with interval and ratio, it is possible, but it's probably going to be a little bit harder simply because when you're dealing with numbers, you tend to have lots of them, and most likely what you're going to have to do is you're going to have to create groups. And creating those groups can be a little bit challenging, but not impossible. Again, statistical software makes this task a lot easier than doing it by hand. So let's see an example here of an interval and ratio type of data. So maybe you run a study looking at daily caloric intake for females age 18 to 34, and your lowest caloric intake of a participant is 1500 calories, your highest one is 3000. So now you're kind of thinking, okay, I need to create some kind of a logical categories that I can classify my participants, right? So now you have all your data in front of you. You found your lowest score, you find your highest score, and then you have the responses of caloric intake of 50, 60, maybe 100 participants, and you need to fit them in those categories. Because imagine it would be totally crazy if you start creating categories of, like, let's just say one participant has 1500, the other one has 1505, the other one has 1560. You would have pages and pages long, and there would be no use whatsoever to actually take advantage of the beauty of creating a frequency table. The idea is to create something very concise, something very easy to read. So in this particular case, what you're going to have to do is create categories. Now, those categories have to have certain characteristics. They need to follow certain rules. One of those rules is that the width within each category needs to be the same. So in this particular case, we're going to see that the width of each category here is 500. And what do I mean by that? I mean that your lowest here, your first category, goes from 1500 calories to 2000. Here you have 2001 to 2500, and here 2501 to 3000. So you can see there's almost like a 500 calorie width in each category. So the width here is equal. The other thing that I want you to pay attention is that there's no overlap between the categories. So I'm not going here from 1500 to 2000, 2000 to 2500. I'm going 2001 to 2500 simply because I never want to have to choose between two categories. So every single category needs to be mutual exclusive. You should never be able to fit data into two different categories. That would be wrong. You would probably double count things, and that would really, really mess up your results. So we never do that. Last but not least is you want to keep your categories to a minimum of 5 with a maximum of 15. Probably you can go a little bit less than that or a little bit more than that, but for sure you do not want to have a lot of categories. The very idea is to have one table that you can view your entire data and not pages long. Once a frequency table turns into pages long, then it becomes very confusing, very hard to read, and it defeats the purpose of having one. Graphs. Graphs are cool, and graphs are usually very beautiful. And we have different types of graphs, and we use them for different types of variables. So the choices are histograms, frequency polygons, cumulative frequency polygons, bar charts, and pie charts. First and foremost, the majority of your graphs, with the exception of a pie chart, is being drawn on an x and a y axis. I'm sure you all know that x is your horizontal bar here and y is your vertical. When it comes to histograms, so histograms are used with continuous data. And how do I know that? What I want you to notice is that all those bars here are touching with each other, right? There's no gap between the bars. That means that in order for this to happen, all the numbers on the x-axis has to be continuous. That means you can have fractions or decimals. The y-axis gives us the frequency. So this is your highest frequency, and this is will define the height of your distribution. And since we are having continuous type of data, that means that histograms are being used with what type of variables. They have to be measured at either interval or ratio level of measurement. So you would never use a histogram with nominal type of variable. Frequency polygon. These are very much related to your histograms. The only difference is that you find the midpoint of each bar. Once you identify the midpoint of each bar, you kind of like draw a little dot in there, and you go ahead and you connect the dots and you draw a continuous line. Okay, so once again, in order to have a frequency polygon, you would need continuous type of data. So we're talking about interval and ratio. Now, what are some possible shapes that you can have for histograms and frequency polygons? The two most common ones that you will see, they're either going to be a unimodal distribution, which means you have one mode right here, it's this natural bell curve, or a bimodal distribution. This is a very common one where you have two definite modes, and you recognize that because you have two humps, okay? Cumulative frequency polygon. Uh, these are actually very handy anytime you want to see what's going on with all your respondents. So here, for example, we're testing for calcium measured in milligrams per deciliters of blood, and you can tell that very few participants here. This is, I guess, your frequency, and this is your calcium. It's an increasing line. You see how as you keep increasing the number of your participants, it keeps going up, 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 and then it levels off here. So you reach your max point. So here you keep adding the responses of each frequency, and it created like this beautiful S-curve, which is a good thing. Now, anytime that you add your responses, it's always going to add to almost to 100%. Bar charts. Bar charts are very frequently confused with histograms. Please look at the picture and try to figure out what's the difference between the two. So they both have bars, but the bars in the histogram were touching each other. The bars in the bar chart do not touch each other. You can see this is one category, a second category, and there's gap between the two of them. When it comes to drawing a bar chart, usually again in the y-axis we're going to display the frequency, and in the x-axis we're going to put the categories. We only use bar charts with nominal, maybe sometimes with ordinal types of data, but we're never going to use it with continuous. And can you see why? If your numbers here were continuous, they would be touching each other, so that means this would turn into a histogram and would no longer be a bar chart. Pie chart. Pie charts are beautiful, and they're unique in the sense that it has an added benefit. Besides giving you this beautiful visual of what's going on with your data, it also provides you with the benefit of giving you, like, this category, what part of the whole it represents, right? So this is your entire data set, and you can see what part of the whole is this 32% right here, right? I'm not sure what that represents, but it can be anything. It can be ethnicity, it can be anything. Pie charts can pretty much used with any type of variable. The only rule that you need to apply here is that you will only use them when you have few categories. For sure, you do not want to have a pie chart when you have several categories, because then what you're going to end up with is a pie chart that has tiny little slivers, which is going to be very difficult to read and will defeat the purpose of designing one. So what are the rules to a great figure? This is literally straight out of your book. So how do we design great graphs and great frequency tables? Uh, the top thing that you need to have in your mind is you want to get rid of all the junk. Again, the idea is to communicate one idea and only one idea at a time. Quite frequently, we have the tendency to just want to put more and more information simply because we think more is best. But the thing is, by adding all this extra information, sometimes we make it very difficult to read. And that is not the point. So, a very good researcher, what is going to do is going to think what is the main idea that he's trying to convey, to communicate, and then it's going to think what type of information needs to go on that graph or on that frequency table that would really support that idea the best. You need to keep it simple, you need to keep it clean, okay? Even the formatting, you do not want to have way too many lines. You're going to see that if you do APA formatting, for example, for frequency tables, you're not going to see any vertical lines whatsoever. You're only going to see a few horizontal lines. The idea, the concept behind it is to keep it as clean and not busy as possible, okay? Again, another thing is that you need to identify everything. But by identifying everything, I mean to simply label everything. So someone that has no idea what you did is going to be able to read it and understand what's going on. But at the same time, you do not want to put way too many words. You're not writing an essay there. So you need to be very picky as to what types of words going to go into your graphs and how you're going to describe them. So keep it simple, keep it clean. Now we're going to talk about differences between distribution. So distributions can differ greatly from one another in several ways. And the question is, well, how do we determine that? There's different ways that four different criteria that we use to identify those differences. One of them is the average value. The other one is variability or dispersion, skewness, and kurtosis. Average value. So why this is useful? Well, let's take a look at this picture. What do you see? You see three bell curves that, at least to me, they look identical. They seem to have the same height. They seem to have the same width. So by just simply looking at them, you would derive in the conclusion that they're the same. But if you look at their average, and what I'm talking about average here is literally calculating the mean, you're going to see that they're no longer the same. Because remember, this is your x-axis, and as you keep moving towards your right here, the numbers keep growing, right? They keep increasing. That means that the average value for the C distribution is greater than the average value for the B distribution, and the B distribution average value is higher than the average value of A. So although the frequency might be the same, and that's why they have the same height, although the variability might be the same, because that means they have the same spread, the same width, the average value differs, okay? So when we're examining distributions, we need to take always into account the average value of the distribution. The next thing that we need to take into account is variability, dispersion, okay? How dispersed our data points are from one another, or how closely together are they. Here we have the opposite example from comparing to the previous one. Here we're having three distributions that look completely different from each other, yet they share the same average. So you calculated the average for all three distributions and you found the same number. But there's no way that those distributions are the same. I mean, they look different, right? although they share the same average. The reason is that the variability among those distributions is very different. So let's take it one by one and see what's going on. In distribution A, which is this tall and skinny one, you would conclude that the majority of your responses are very close to the mean. So as you can see, the majority of the response go here, and then as the tail opens up here, there's not too many. So this is a very low frequency here, the ones that goes towards the tails, which is going to be your extreme scores. So the majority of the responders in this particular distribution, uh, they're very close to each other. They're very close to the mean, and that's why this distribution is very long and tall and skinny. In distribution B, you have a nice spread. So this one, distribution B, looks kind of a normal distribution. So that means that the variability is as normal as to be expected. And that's why it's not very tall, it's not very short, it's not very wide. It looks pretty normal. On distribution number C, though, look how flat the top looks. That means that you have a lot of responses with very high frequencies, which turn that top part here very flat. So distribution C would say that it has the highest dispersion. It has a lot of variability, and that's what caused this distribution to be like kind of like short and wide. So the ways of describing the distributional shape would be central tendency, which we just covered, dispersion, which we just covered, and also modality, skewness, and kurtosis. So especially for skewness and kurtosis, these are going to be two things that we're going to have to start taking the mean and the median into account, which means that when it comes to skewness and kurtosis, it's not going to apply for nominal, because remember, nominal are categorical, so you're not going to have numbers there. So if you don't have numbers, there's no way of calculating a mean. You're simply going to have a category, female, male, and you're going to have a frequency of how many males and males there in each group. So there's no way you're going to calculate skewness and kurtosis. So for nominal, the only thing, extra thing that you can evaluate would be modality, the frequency of how frequent something appears. When it comes to ordinal and interval ratio, since here we start having numbers, especially for interval and ratio, that means we can calculate skewness and we can calculate kurtosis. Of course, you do not know what those are yet, but we will cover it soon. So modality, what is modality and how does it differ from calculating the mode? You all know how to calculate the mode, right? It is the most frequently appearing score in the data set. So modality, in a way, it's similar, but now you're simply observing in your distribution, and you're trying to identify peaks within your distribution, and that's why I put this picture right here with mountains. So here you can see you have 1, 2, 3 peaks, right? So this would be a tri-modal distribution. These are some more examples of modality. This is an example of a unimodal distribution. Unimodal means one mode. This is an example of a bimodal distribution. You can recognize it because, again, it has 2 humps. This is modality with nominal variables. Here you have ethnic distribution. So Puerto Ricans apparently win here. So this is your one mode unimodal distribution, with Puerto Rican being the highest frequency. In this particular example here with programming language, we see that we have 3 modes going on. So you have the C++, you have the JavaScript, and you have the Ruby. So this is a tri-modal distribution. Skewness. What is skewness? Skewness has to do with the degree of symmetry. So you look at your distribution and you think, well, how symmetrical is it, or how off-center is it? if you have anything that is off-center, that means it is skewed. Skew can go to the right, a skew can go to the left. It does not matter. It's just a matter of being symmetrical or not. So this is how the different skews look like. It is very important to be able to identify if something is a negative or a positive skew, so pay attention to this in the next slide that's coming up. So on your left here, this is a normal distribution. It looks like a bell shape. So it has no skew whatsoever. No skew means that your mean is equal to your median is equal to your mode. This is going to be a negative skew, and it is a negative skew because the tail here, you see how it drags towards the negative side? So imagine this is your x-axis right here. This is the negative side. This is the positive side. So wherever the tail goes, that means that's the type of skew that you're having. So since the tail here is dragging towards the left, that means this is a negative skew. Since it is going to the right, this is going to be a positive skew. How do we calculate skewness? The easiest way to calculate it would be mean minus the median. So if your mean is equal to your median, that means your simple skewness is going to equal to 0. Equal to 0 means no skew. If your mean is greater than your median, that means your simple skewness is going to have a positive result, which means you're having a positive skew. If though your median is greater than your mean, that means you're going to end up with a negative simple skew as result here, which means that you're going to have a negative skew. Again, let's take a visual of what we just described. So sometimes people are able to figure out just by simply looking where the tail is going and identify if it's a positive or a negative skew, or where the mean is at, simply by looking at the tail. Usually the mean is going to be wherever the tail goes. So as you can see here, the mean is greater than your median, so that's why it's pulling towards the right side. Here your mean, which is a negative skew, right, is less than your median, and that's why you're having a negative skew. Kurtosis, that is another funky term that you need to know. So kurtosis has to do with the height of the distribution, how tall a distribution is. We can see here again we have a very tall distribution, an average distribution, and a very flat distribution. In statistics, we use different terms to describe kurtosis depending on how tall or how short they are. Those are platykurtic for something that is very flat and very wide. Platy in Greek means wide. Okay, so platykurtic is going to be a very wide, flat distribution. Kind of remember this wide nose. Okay. Leptokurtic, leptos means skinny, so it's going to be very pointy. Okay, very picked comparing to the normal distribution. So a normal distribution is called a mesokurtic distribution. Meso means average, so you're an average height, so there's nothing extreme about it. It's not platy and it's not lepty. Now, how do we calculate kurtosis? Your book has a very fancy formula that I definitely do not want you to memorize. You don't have to even read about it. You can just skip through that section. Instead, when the time comes, we'll use SPSS to calculate it. So do not worry about it because SPSS does a wonderful job calculating both skewness and kurtosis. In general, though, how we're going to figure it out is that anytime you're asking SPSS to calculate central tendency or variance, it's going to calculate the test statistic for you, and also is going to figure out the standard error. And what you're going to be looking and comparing is the test statistic to the standard error. And if the test statistic is twice the size of the standard error, then you can conclude that you have a significant skew or kurtosis. Again, not worry about this right now, just know the very basic rule of it. Box and whisker plots. Box and whisker plots are very handy tools. They are pretty much what they are is a box with two lines going from on either side of it, which called the whiskers. And the reason that we're using them is in order to get a quick visual of how our data looks like. So we just interview a bunch of people. We go ahead and we ask SPSS to create a box and whisker plot, and right away we can see if we have any outliers or where the majority of our data is concentrated. Again, box and whisker plot is just simply one of the tools that we have. There's others, but uh, box and whisker plots are used a lot, and they're quite easy to even draw by hand. What you need to find out is what is called the quartiles or your medians. So you're going to have apparently the lowest score in a distribution. You're going to have your highest score, and then you need to find your middle point, your median. So in where the median is, you're going to draw a line that is going to become what is called the Q2. Then you need to find the middle point between the median and the lowest point. Where that middle point is, that's going to become your 25th percentile or your Q1. Then you're going to find the midpoint between the median and your upper score, and that's going to be your 75th percentile or Q3. So Q1, Q2, and Q3, this is where you're going to draw those vertical lines. You're going to connect them and you're going to create a box. And then from there, you're going to connect the line from there to the lowest and highest score, and that's going to be your whiskers. And what that does is, like in this example, for example, we can see that the left whisker is a lot longer than the right whisker, which pretty much tells me that I have an outlier somewhere out here. Also, by looking at the box, I can see that my median or my Q2 is pretty centered between my lower quartile and my upper quartile, so it's pretty balanced. There is a possibility that your median might be somewhere in here. That means it's concentrated most of your values somewhere in this area. So again, you're using the box and whisker plots to get a quick visual of what's going on, and depending what you see, you might decide as the researcher to make various adjustments before you proceed to further analysis. In summary, okay, so we can display data using tables and graphs. Our four most commonly used types of graphs include histograms, bar charts, frequency polygons, cumulative frequency polygons, and pie charts. The way we decide to use any of the above will be based on the level of measurement of the variable that we're having in front of us. And distributions can vary in terms of average value, variability or dispersion, kurtosis, which again has to do with the height, platykurtic being a very wide distribution, leptokurtic being very skinny distribution, and finally skewness, which has to do with the level of symmetry. Review question. Which variables are ideally suited for use in a pie chart? You got time of the day, ethnicity, and you got age groups. So you want to create a pie chart. Out of those, which one do you think would be your best bet? You guessed it. It is ethnicity. Ethnicity is going to be your best variable in this particular case to create a pie chart, simply because you have very few categories, and it would be a wonderful way of displaying the various ethnicities in a pie chart. So you would have, for example, white, Latino, Asian, other, and you're going to have little slices, and then you'll be able to see which part out of the whole is Latino, or Asian or whatnot. Okay. Last question. Which type of distribution does each of these graphs have? So what do we have right here on our left? This is a normal distribution. It is very much so symmetrical. Here you're having a skew as well as here, but this one is a negative skew because the tail goes to the left. This is a positive skew because the tail goes to the right. So this is it for today. You have a wonderful rest of the day, and we'll talk again next week. Have a good one. Bye.